Hi and welcome to Physics High, and today I want to explore an overview of modern physics. Now, what is modern physics? It's a fairly nebulous term. There are a couple of ways that we can look at it. Number one, we can look at it as a way simply as a physics that's developed in the last 120 years. And generally speaking, modern physics really started around 1900. Another way of thinking of modern physics is the way that it's a new paradigm. The old paradigm of classical physics, where waves and energy was discrete to the physics of mechanics, that is the motion and analysis of motion of particles, means that modern physics blurs the lines between those two. But the reality is that classical physics still holds sway in many of our everyday experiences. And the third way we can look at it is simply by looking at the extremes. In other words, we're going outside the realm of our everyday experience. We look at the physics of the very, very small and the physics of the very, very large. So as a result, I'm going to be building a concept map of modern physics based on those two categories. Start. Let's look at the very small, and I'm going to be just simply calling the idea of the quantum. In other words, it's the physics of the very, very small. The other way that we're going to be exploring in a moment is the idea of relativity, which is the physics of the very, very large. Now, what I'm going to do is I'm going to explore a whole range of concepts that are related to modern physics in terms of the very small and the very large, but I'm going to do it chronologically so we can see sort of the development of modern physics over the last 120 years. Now, like all concept maps, I'm not going to go into great detail on each of the particular points. Now, in most cases, I have videos that deal directly with each of the points that I will discuss in terms of modern physics, and I really encourage you to have a look at my work where I cover each particular point in greater detail. But before we look at the chronological order, let's have a look at the key disciplines within these particular areas. One key concept is what I refer to as the wave-particle duality. The second idea I'm going to be looking at is nuclear physics. Then there's atomic theory, and finally, particle physics. In the terms of relativity, we're going to really divide this really up into two areas. The first is the idea of special relativity, and I'm just going to word the word special, and then there is general. So now that we have our key disciplines, let's look at a little bit of the chronology. As we look at the various aspects there, we're going to see that they're also very interconnected. Now, the first thing I do want to highlight, though, although not strictly in aspect of modern physics, is James Clerk Maxwell. And in terms of that case, I'm going to write the name Maxwell up here. James Clerk Maxwell developed the theory of electromagnetism by combining the various laws related to electricity and magnetism. He developed this theory of electromagnetic radiation, and as a result discovered that the speed of this electromagnetic wave was a constant value and was now known, of course, as the speed of light. Now, why do I have that there? This was around the 1860s. Well, that's actually quite a key point here to understand special relativity, which I'll touch on in a moment. The other thing I want to make a note of is the experiment by Michelson and Morley. Now, Michelson and Morley did an experiment to detect the presence of ether, that is, the light speed will change depending on the motion of the Earth, and it was a null result, and as a result caused great problems because there was the expectation that ether existed. Now, although Michelson-Morley's experiment wasn't important in terms of Einstein's thinking when he developed his theory of relativity, both special and general, it's an important point to remember that this feeds into our new understanding of modern physics. So let's now move on. This is the 19th century, and now we're going to go first in the 1890s. And I'm going to start off with the discovery of the electron. J.J. Thomson discovered the electron, and he discovered that this was significantly smaller than the smallest known atom at the time, which is hydrogen. And so as a result, we have our first introduction to the idea is that an atom is not indivisible. In other words, it's made up of smaller particles. And as a direct result of this, what we now get is a model of the atom that went into what we refer to as the plum pudding model. Now that model was an atom that basically was a positive sphere with electrons embedded in it. But that particular model had some significant problems, and we'll look at that in a moment. Also in the 1890s was the discovery of radioactivity. The first person, of course, was Henry Becquerel. But then also, subsequently, as we go into the 20th century, we have the Curies, who examined radioactivity more closely and subsequently discovered radioactive substances such as radium and polonium. And then in 1900, we have the first real break in terms of classical physics. And here what we have is the study of blackbody radiation by Max Planck. Now, Max Planck was examining blackbody radiation, and he made a premise that energy is quantized. So by treating, at least mathematically, that energy came in discrete amounts, we have this idea, this thing that we call energy has a particle-like nature. It's discrete. And that was done in order to explain the black body curve. Now, why is this significant? Well, it's significant because now we come to 1905, and in 1905 we have Einstein's seminal year. We call his miracle year, where he published 5 key papers. And in 1905 we'll see that our board will start to light up, so to speak. The first thing is that Einstein was able to explain the photoelectric effect by the idea of energy being quantized. And the formula, of course, that we all know, that we should know, is E equals hf, that the energy of a particle of energy is related to the frequency. Now is our wave-particle duality. Now he was treating light with particle-like properties, and we now refer to them as photons. Also in that year, he basically, by thinking through the significance of Maxwell's premise that light is traveling at a constant speed, irrespective of the observer's motion. And as a result, that gave us 2 key outcomes. The first outcome was that time, momentum, and length were relative. And the second key outcome is that energy and mass were equivalent by that mathematical relationship. In other words, that energy and mass are in essence the same thing. Let's move forward in time. In the latter part of the first decade of the 20th century, Rutherford was interested in testing the plum pudding model, and by the famous experiment by Geiger and Marsden, where they were firing alpha particles, which were emitted from polonium, which was of course discovered by the Curies, he was able to demonstrate that the plum pudding model wasn't actually a valid model. And he came up with a new model, and that model is often referred to as the planetary model. Now that's a model where you have our atom made up of a nucleus where most of its mass is actually concentrated and the electrons are in orbit. And that was a model that was developed based on his experimental analysis of the scattering experiment or the gold foil experiment. But that model had some problems. Now, related again to the idea of Maxwell over here is that if an electron is moving in orbit, it should be releasing electromagnetic waves. It should be losing energy and the electrons should be spiraling in, but it doesn't. So that can therefore moves us to 1913 with the Bohr model. And Niels Bohr developed a model that the electrons existed in discrete orbits. Here's that word discrete again. So now we get again this idea of quantization, that the energy that the electrons have discrete values. So they can exist in one orbit but not in the other, and so forth. So in other words, we now have again a development of this idea of discreteness of quantum in the structure of the atom where the electrons exist in specific orbits. Moving on to the second decade of the 20th century, so around 1913 to 1915, Einstein, having developed his special theory of relativity, which is really about looking at relativity in an inertial frame of reference, so there's no acceleration, he extended it by considering accelerated situations. And as a result, he came up with this new concept of gravity and also the idea of space-time. The idea that gravity wasn't a force, but gravity was a distortion of that space-time. Now, what's the evidence for this space-time? Well, not long after his development of his theory of relativity, in terms of general theory of relativity, there was a solar eclipse which was necessary to see if light from a distant star behind the sun could be distorted by the gravitational effects of the sun. And so what we now have is this concept of gravitational lensing. By the time we get to 1919 and 1920, we have a confirmation of Einstein's theory of relativity through this particular evidence right there. Also occurring roughly around this time were two other key experiments. One of those experiments was done by Robert Millikan. Now, Robert Millikan was particularly interested in the actual value of the electrical charge that the electron had. And so what he did was a very famous experiment, which is often referred to as the oil drop experiment. And what he did there was actually determine the electrical charge, and he determined that this charge was discrete. In other words, anything that was electrically charged was always a whole number of the elementary charge, that is 1.6 by 10 to the negative 19 coulomb. And in other words, the charge on an electron is nonetheless also discrete. In the early 20s, we have another experiment, and in this case, we have Arthur Compton's experiment, which is referred to as the Compton effect. Now, what is the Compton effect? What Compton did was he fired photons of X-ray light. In other words, he presumed that they existed as photons, and he noted that when he fired at the crystals, that electrons were scattered off it. Now, what does that mean? Well, that means that the photons had momentum and so therefore had particle-like properties. So you can see now what we have here is this whole idea is that what we considered as a wave, in this case, X-rays, actually had particle-like properties. Back to our Bohr model over here. And if you remember, Bohr had a model of discrete energy shells, but how to explain them? Now, this now introduces de Broglie. He surmised that the electrons could stay in discrete orbits if we treated them as standing waves. In other words, they can remain in the same energy level if they are in resonance. Hopefully, what you can now recognize is that de Broglie's hypothesis that electrons have wave-like properties basically is the other side of the argument of the wave-particle duality. That is, we can have waves that have particle-like properties, but now we can have particles that have wave-like properties. So hence we have the wave-particle duality. And that was again extended first by Schrödinger, but then also Born, where we have the idea that electrons exist as probability clouds that can be described as waves. In other words, the probability cloud is actually a wave structure. So we've moved a long way from the discovery of the electron to our understanding of the atom in terms of the model that has changed, and yet the time frame here is roughly 30 years. And now we come to the 1930s, and what I want to do is explore a little bit about the development of particle physics. But before we start, we need to also look at two key technologies that were used to understand the nature of the atom at the time. The first is the cloud chamber, and this, which basically is a very saturated area of either, in this case, alcohol or gas or so forth, that allow the tracking of charged particles as they move through them. And the second one is the idea of particle accelerators, which were basically the cyclotrons, and then later in the 40s, the synchrotrons, which allowed scientists to speed up particles and collide them with the things that they wanted to examine. In other words, they were doing scattering experiments, similar to what Rutherford did with alpha particles, but now at much greater velocities. And why do I mention this? Well, it's important because in 1932, we have James Chadwick discovering the neutron, and as a result, the scientists believed that basically all particles could be described as a combination of the neutrons, which were, as I mentioned, in 1932, the proton in 1919, and of course the electron in 1897. But then in 1932, we have the first evidence of a particle that was positive in nature but had the properties of an electron, and we now know that as a positron, and that was detected through cloud chambers by Carl Anderson. And in 1937, Carl Anderson also used cloud chambers to show the existence of a muon, which pretty much had every property of the electron except that was significantly heavier. And as a result, in the 1930s and following the 1940s, we had this idea of what they called the particle zoo. Now, the particle zoo really is an explosion of particles were being detected that could not be explained using the model of the electron, proton, and the neutron. And so that created a great problem in terms of what is the fundamental nature of matter. 1930s as well, we have the understanding of nuclear fission. So with the work initially of Enrico Fermi in the early 30s, 1934, and then later Lise Meitner and others, they understood what nuclear fission was. And nuclear fission, of course, is where the nucleus of an atom is split into two and releases energy. Now, why is that significant? Well, that actually ties in with E equals mc squared. The mass that was lost in the process of the splitting was converted to energy. So it actually, the understanding of fission was actually a confirmation of also of E equals mc squared, the relationship between energy and mass. And then subsequently, of course, we also have our understanding of fusion at a later date. And now let's move a little bit forward in time in the early 1960s. So we have all of these particles that were detected but could not be explained. And as a result, a theory or a model came about which is now referred to as the Standard Model. Developed by Murray Gell-Mann in the early 60s, it was a model that looked at the properties of the various particles, and by hypothesizing that protons and neutrons were actually made up of smaller particles called quarks, he developed a model to explain all the other particles that existed in both combinations of ordinary quarks, of now which there are 6 flavors, but also the antiparticles, which are the antiquarks. And then in the late 60s, we have QED. Now, what's QED? It stands for quantum electrodynamics, and it unifies the theory that underpins the Standard Model with the special theory of relativity. So in other words, we now have a connection that goes across there. The Standard Model has since developed, and we now have a model referred to as QCD, which stands for the quantum chromodynamics, which underpins the theory of how quarks and the gluons that hold protons and neutrons together interact. Again, this is quite complex, but nonetheless, we have now a theory that explains the behavior of protons, neutrons, and other types of baryons. So here is our concept map, but all of this is interconnected, and I've already started mentioning a couple. The fact that we have de Broglie and Schrödinger here is the fact that electrons have wave-like properties. So we have a connection between these two areas. Cyclotrons and synchrotrons are particle accelerators. They rely on the momentum of our particle increasing as they approach the speed of light. And so we have a connection between these two. In other words, the theory of special theory relativity is important in the working of cyclotrons. As I've mentioned, fusion and fission both are concepts related to E equals mc squared. So those two are also interconnected. And there are others, of course, I can draw out. Now, I will finish, however, with still some questions. And that is that this story isn't complete in terms of modern physics. There are still many unanswered questions. For example, why are there 3 groups or 3 families within the Standard Model? Secondly, what about the existence of dark matter? What is dark matter? Well, we don't know. We can detect its gravitational effects through gravitational lensing, but it doesn't emit or absorb or reflect any electromagnetic radiation. It doesn't interact with normal energy. And so as a result, there is a lot of work done in particle physics to explain the existence of dark matter. And then we have the idea of antimatter. Again, Particle physics shows us that antimatter exists, and our understanding of cosmology is that there should have been roughly equal amounts of matter versus antimatter in the early part of our universe, but it doesn't exist. Where has all the antimatter gone? So there are still many questions that need to be answered. Well, I hope that has given you a good oversight of what is involved with modern physics, and if you want to explore any of the key points here I've mentioned in greater detail, please check out my other videos.